All right, so in this video, we're going to be looking at smoothing methods for dealing with time series. In a previous video, we looked at ARIMA methods, and so now this is a different approach for dealing with the same kinds of data. Now, for this example, we're going to start by loading a couple of packages. As always, if you haven't ever used these packages before, you'll need to go to the Tools menu and install them. We're also going to use a package called FPP2. One of the data sets that we're going to use later is coming from this package. And we're going to use two sets of data for our example. One is Google data, and a second data set will be on airline passengers. So this is on, this Google data is on their stock price. Now, when we do testing and training sets for time series, we don't separate them randomly. Instead, we have to separate them in time. And use older data to predict future data. So we use the first, let's say 80% of the data, and then we use the second 20%, the final 20% of the data as the test data. And then so similarly, now when your data is separated into year and month, then you have to use this vector configuration in order to get the exact time, the year and month that you want. So we're going to start with a smoothing model where we can specify the degree of smoothing on our Google data. Alpha is the degree of smoothing variable, and this is something that you may need to experiment with in order to get the right amount of smoothing in your model. And so this one forecasts from simple exponential smoothing. This is our initial time series for Google stock data. And then this piece out at the end is the exponential smoothing forecast. Now you'll notice that the forecast is basically constant with obviously ever increasing standard errors as we go out in time. This suggests that we're not really capturing the trend. And so what we can do is we can try using a differencing approach in order to see if we can extract the trend. So that looks reasonably stationary, a couple really big spikes, but otherwise fairly stationary. Now, if we calculated the differences, for the training set, we're also going to need to calculate the um, differences for the test set. And I had a typo, so I'll re-enter that. So I don't have to keep carrying it going forward. Letters are right next to each other. Let's see. I see I skipped a step. I'm calling a function I didn't actually calculate. Uh, we have to model differences. Okay, so here's our differences and here's our predictions. And so then we want to compare our test data to our training data and see how well our predictions do from our model. And the accuracy calculation outputs several measures of accuracy that we can check. So we've got a mean error, we've got an RMSE, so the root mean square error, we've got an MAE, we've got an MPE, an MAPE, and so many different ones. You can use the one that again, that you are comfortable with. They all kind of are measuring the same thing. But we have different measures of accuracy that we can use. The root mean square error is sort of the typical one, or some people prefer the mean absolute percentage error, for instance. Now, if we want to test different values of alpha to see if we can improve our model, then we can do that by creating a vector and running that through a sequence of values. So if I start at 0.01 and I go up to 0.99 and I go by 0.01, I can create a value for collecting my root mean square error and then do a little for loop. And so here we're collecting our alphas and our root mean square errors as an example accuracy measure into a data frame, and then we are going to find the minimum value of alpha, the value of alpha that produces our minimum root mean square error, and then we're going to plot the results. If you haven't already, we need to load ggplot so that we can make a graph in ggplot. And so this is the value, this is our line graph of our alpha values and the RMSE that they calculated. And the minimum value is actually way down here at a very small value of alpha. So we've essentially tested like 100 different values or so of our alpha value and found that the smallest value actually does the best job. And now we can actually use that in our model to get our best model fit, our optimal model fit. So it's something like 0.05. It's something quite small. It might be smaller than that, but you can actually print out the value and find out what it is. I'm going to kind of eyeball it for our example. And we can see for the test and training sets, we're getting fairly similar results in most of these cases. Our MAE, our MASE are very similar. And then we can create some graphs. So we're going to create the optimal model. Plus, we're going to add a theme. And so now we're going to plot the two graphs side by side. And again, we're getting basically a flat prediction, even though our test data is, of course, noisy. It does seem like our prediction is basically staying near zero, and our actual differences are also staying essentially near zero. So it's not terrible in the sense that it is capturing the general trend such as it is. It's not obviously predicting the noise, but it is predicting the overall pattern of these differences. Now we're next going to look at Bayesian smoothing methods. So we're going to load another package, the BSTS package. And here we're going to look at another data set called iClaims. So we've specified 52 if they're weekly claims, weekly seasonal data. Uh, Obviously, you would do 12 for monthly. Now here we've selected a state space for the model and using a linear trend. You may want to graph the data, of course, first in order to determine if a linear trend is the best thing. As I said, we selected 52 because it's weekly data, and now the model is being fit using a Monte Carlo method for 1,000 iterations. And now once the model is complete, we can go ahead and plot the model. And we can plot the components of the model. So we have the trend and we have the seasonal component. Now we can also, of course, then use this to make predictions. And we'll go out 12 steps. And then we can plot and so we've plotted the original data and then we've plotted the predictions on top of that data. Now, a nice feature of the Bayesian smoothing method is that we can then add additional variables to our model. And while that's running, now in this case, we predicted the expected model size because when you don't specify that, it just does one value. And so now we can plot both of these. And we'll plot the components, trend, seasonal, and regression. And again, trend, seasonal, and regression for our two models. We can also plot the coefficients. Not model one, model two. And so we get that our largest coefficients are the unemployment office and filing unemployment, it looks like. And we can also plot model three. Yes, and the first two, these are the biggest contributors to our model. And in fact, if you zoom out, you can actually see that the unemployment office is actually the first variable, and then the one that's not actually being displayed, it's only displaying every other value. Idaho unemployment is the second largest coefficient, followed by unemployment filing, and so on. And indeed, you can back up to the previous one, and if you zoom out to that, Idaho unemployment is also the second largest bar. Now, if we want to compare our models, we can compare our BSTS models. And we can run that. And so our legend is kind of in the way, but you can see we have our black model is model one, and our red and blue models are from the differencing, that's models 2 and 3. The last example we're going to look at is for the LOESS seasonal trend decomposition using LOESS, the STL model. And so we're going to pull in one more data set. This is from the FPP2 package. And we're going to do a little bit of piping. And then we're going to plot it. And so we see our decomposition, our original data. This is our trend. This is our seasonal component. And then this is our error. And then one last thing, we're going to plot one more graph based on this data set. Now the MSTL function will do basically the same thing. It has some reasonably good defaults, so it actually doesn't require us to put in quite as many attributes in order to get fairly similar results. The difference in the remainder part in the plotting, you can see that they plot that as a line graph rather than a sort of a bar graph of sorts. But otherwise, you can see that the decomposition is actually quite similar, although obviously not exactly the same. Now, this is where the applied statistics lectures end. I do have some other materials that I will probably post in time. I also teach data mining and data exploration and machine learning courses, the same place that I teach this material. And so I do have some other things that I'm going to add for those topics in time. But this is the end of the R code that my applied stats students learn in an entire year. So more to come, but there will probably be a pause in time before more things get added.